Hello there. Welcome back. Sorry about any delays, but I'm sure that any delays on my part could be used, or it could be time used by you to continue reading this manual. I'd like to go on to discussing exceptions, but I'd like to point out anyway that an exception of the kind that I'm going to be talking about is something that happens in a sort of asynchronous way. Something unexpected occurred. Okay, that idea of an asynchronous function call, that is, a function gets called, but you didn't call it. As far as you know, nobody else called it. That is similar to the idea of an interrupt. In particular, the kinds of interrupt calls that get generated by an external event, like a keyboard press, right? The processor and the computer and nothing in the machine knows that you're going to press a key. So what happens is something called an interrupt gets generated. If you remember back in DOS, there's a table at the beginning of memory, segment 0, offset 0, and it goes on all the way up to 400 hex. Oh, whoops, I went past it, all the way up to here. Is that right? Yeah, there are 100 possibilities, hex, from 0 to FF, and each one of the entries in this table is 4 bytes long, and it's a function pointer. Each entry is a function pointer in real mode, so that means segment and offset. Actually, I might fill up the whole screen. I guess 3FF. Yeah, it went past. Almost big enough. I'll go to, I'll just dump to 2FF. Okay, well, good guess. So this is what part of the DOS real mode interrupt table looks like. Okay, just a bunch of function pointers. It actually does. It's clear that after this point, it's just repeating itself, and so this is probably garbage. But these other ones have meanings, and the meaning is a function address. Now, when you press a key, something happens with the hardware, and the hardware responds by invoking one of these functions. Just suddenly, that function is entered, and the CPU, no matter what it's doing at the time, suddenly finds itself executing code at a completely different spot, right? Now that's asynchronous. That's not predictable. But the interrupts themselves, the functions, the programmer can call those functions as well directly. Like one of them is never used in response to an external event. So they call it a software interrupt, like int21 for instance. For DOS, you use this. The programmer uses this interrupt mechanism to call into the operating system kernel, to call functions and services provided by the operating system directly. And the reason you use this interface rather than function, let's say a standard function address, is because probably they decided to use this mechanism because with each version of the operating system, the position of let's say the entry point to the operating system might change, right? But if they use this mechanism, then you add a level of indirection, and all you got to know is the number 21 and the particulars of the sub-function that you want to call. Okay. Now, this manual talks about interrupts and exceptions as separate categories, which they are. And in talking about it in this early chapter 2, they just make this distinction, okay? And they say that interrupts are asynchronous, okay? Which, if you want, you could take that as the definition of an interrupt, and that's a better definition than saying, that's a function listed in the interrupt table, because this is clear. There's only one possibility. Asynchronous. If you use the definition that I just said, then interrupts could be synchronous or asynchronous, and that would be confusing. However, going further in the manual, I come back to this topic. I think I put a bookmark on it here, I think. No, not there. Let's see, exceptions and interrupts again, right? All right. Now they're being a bit more specific about defining these terms when talking about these two categories of things. The words, the wording interrupt and exception correspond to special kinds of control, what they call control transfer. That is an alteration of the program flow control where IP is pointing to and what the environment is. And they're analogous to what we call here like an unprogrammed call, right? So that is actually a very good analogy. It's like a function gets called, but you didn't write any code for that function to get called, so it's unprogrammed. Normal program flow to handle. Normal program flow stops, right, in order that external events or exceptional conditions be attended to. Now they're distinguishing between interrupts and exceptions. Interrupts, as they defined, the asynchronous thing, as they've defined them as asynchronous, are events that correspond with events external to the processor, like I press a key on the keyboard. Exceptions are not external to the processor. They're generated by the processor when it detects some kind of exceptional condition that has arisen. So it's executing, the processor is happily executing instructions, and perhaps it sees some condition that requires immediate attention, and then it generates an exception, something called an exception. Now, as far as external interrupts, okay, now whenever they're talking about interrupts, they're not talking about 21. Okay, in this manual, an external interrupt is not, has nothing, for instance, there's no interrupt table, so you can't even say int 21, right? You can't have this table of real mode function pointers. Oh, and that reminds me, I think I even put this in, I even intended to put this in the title of the video, and that I wanted to add something to add an addendum, whatever the word is, to make an addendum. I wanted to addend to the last video that there isn't, of the descriptor tables, there is another descriptor table that is required, at least one, because there's no interrupt table available. Right? I mean, this one, the one in DOS, that your machine currently started out, it's the session, it started out in real mode and was using that table, and that eventually got discarded, and now you're in protected mode in some virtual machine land. But at the beginning, whenever you turned your computer on, there was an interrupt table being used, and it's been thrown away. So how now is the machine going to deal with you pressing something on the keyboard? The way it does that is through another type of table, and that table is in fact called a descriptor table. It's called the interrupt descriptor table. So in addition to the global descriptor table and local descriptor table categories, as you saw, each process gets its own global descriptor table. There is another descriptor table called the interrupt descriptor table. All right. And that's for handling things like keyboard presses. Now the entries don't, the entries in this table, wherever it is, are called descriptors, and here's what they look like. And there are three types. You'll notice that as far as offset is takes up the whole, the first two and last two bytes for this particular one anyway of the descriptor. So that's different. And same for this one. And this one has no offset associated with it. This only uses a little bit, a selector value. and some flags, and these two things are still valid, present or not. Okay, so these ones correspond with offset, selector offset, like regular descriptors. These ones have no address, no offset associated with them, I should say. Just actually, there's only what, 1 byte worth of information for this 8-byte structure. Oh no, sorry. There's a selector and 1 more byte for this one. So there is another descriptor table in the world, and there's only one. I'm sure of that. Pretty sure. Well, there has to be only one. There's only one keyboard, right? So I suppose it's possible that you could have a phony interrupt descriptor table on a per process basis, but I don't think it works that way. Find out that there's another table, another descriptor table. Now, getting back to these exceptions, in fact, I wanted to look at that those definitions first. External interrupts, like pressing a keyboard, pressing a key, or me moving the mouse around, there are 2 sources of these external interrupts. What a source is, we'll find out later. Similarly, exceptions are things that have 2 categories of sources. One I just told you about, the processor detects let's say, invalid code, or an attempt to access protected data or something or other, and generates an exception, generates a function call you could say asynchronous, but it's not really asynchronous in the sense of the keyboard, right? It's the computer hardware that has made the detection of and generating this event. So it's not really asynchronous. Although, as far as you're concerned in your program, you didn't call any function and suddenly you're in a different place handling an exception. So it has that kind of asynchronous attribute. Now the programmed ones, okay, are given or are so associated with special instructions. int3, which the debug exception, which you in your program you put them in like that, okay, just as you did back in DOS, is considered to be a programmed exception. Okay, nothing asynchronous about it. Same as int21. Now these things, it says, can trigger exception. These are called software interrupts. There you go. But the processor handles them in the same manner as it handles an exception. So there's a different, it's like a different type of call. Another calling convention, the exception calling convention, if you like. Now, these instructions, these. This is like int21. This is the software breakpoint. These other 2 are new. New instructions. User mode. I mean, not privileged. I don't think so. I know these aren't privileged. I don't think they are. More privilege. I'm not sure what that means. I wish I would say there's a description. How about this into? This just tells you how long. PM must stand for protected mode. Yeah, okay. If maybe this means not protected mode and protected mode. So if you manage to get your computer into real mode, you have to reboot and put a disk in your floppy disk drive if you had one, and load up DOS. Then it takes 33 clock cycles to process just the jump. Whereas in protected mode, this same instruction, CC, which we still call int3, takes longer. And I don't know about this same privilege and more privilege. Oh, I see. If the interrupt is being called and whatever handles the int3 is at the same privilege level as where the int3 was executed, as let's say the thread that executed the int3, then it's faster, it appears. If there's a change in privilege level, then it slows down. I guess. I'm guessing that's what that means. So there's now into. The same privilege, it's more similar to int, like a CC. And it corresponds with interrupt 4. Now it might very well be that these interrupts, like the number, correspond to the entries in the interrupt descriptor table, just like they would in DOS, just like int3 corresponds to entry 3 in the DOS interrupt table. Perhaps that's what this means. There's a selector of some sort that selects just the function, this acts as a selector. It selects the 4th entry in the interrupt descriptor table, and perhaps then puts that into the code segment. It probably is exactly that. Load code segment with the descriptor. As you saw, those descriptor entries were similar. Not exactly the same though, were they? Let's see, here's a descriptor. It's not a regular descriptor, right? The offset part in a regular descriptor had only 20 bits. This is the full 32 bits. So I don't know exactly. I don't know how it works. But I remember that when we did this manually, it wasn't very. The easiest one was the interrupt descriptor table. The easiest descriptor table to set up was the interrupt one, to map all of the interrupts into their corresponding real mode pointers, BIOS and DOS and so on. There was really nothing to that part. It was harder to do the other, to make up the various descriptors for just your code, your code segment and your data segment. We just had one probably. We probably just had one code segment and one data segment, and ES the same as DS. So and the stack segment. I think we made a separate stack segment. It had its own entry in the table. Maybe not though, because we were just trying to get it working, right? We weren't trying to be fancy. All right. Now identifying interrupt. That's these things. One of the things I noticed, exception conditions. If you'll notice about these interrupts, trap gate, interrupt gate, and task gate. Now, exception conditions, this is not interrupts, but exceptions, also fall into three categories, it turns out. Fault, a trap, or an abort. Now, you can sort of guess what these things might be. And they've listed them here as interrupts, as interrupts. Okay. Now these are exception conditions. I don't know. That's not the same as an exception. It's a condition that results in an exception. I think that's the way you read it. In any case, because this isn't online, I've been taking advantage of that fact. It says here, this section describes all the possible conditions and yet classifies each exception as a trap, fault, or abort. And I was looking at it and I couldn't see immediately which ones were traps and faults and aborts. So I added this red here. See what this one's a fault, 6. 6. And I even got a keyboard macro set up. No. Okay. That makes it easier for me to see which are which. Now I don't even know what the difference of these things are, but I'd like to have it in red for when I do understand. This one's an exception. That's just wording, but I think hopefully that clarifies some of the wording. How do we deal with? So we sort of answered this. There are two. This condition, interrupt and exception. It's an exception is not an interrupt. How about that? Good enough. Not an asynchronous interrupt. However, an asynchronous interrupt could be handled by the system and converted into an exception so that the exception handling mechanism can be used to generate a function call. And that's probably what happens. And how do we handle them? Well, to handle them, to handle something like a fault, that is divide by 0, or attempt to access memory, something like that. Use a special keyword called try, just sort of like the C++ try. Remember, for a C++ exception, you said try, and then you put your code in here, and then you had something called catch, right? And this took a parameter, or dot at the end. Once you ran out of things that you thought you might catch, you could put a catch. This is a catch-all. Catch the leftovers. And this here is for catch. Type. Program. Type. Right? That's a C++ mechanism. And that's used for catching C++ exceptions. For catching the kinds of exceptions that are thrown by memory access violations and so on, there's a double underscore that goes here, and this is, I think, the right word, except. And also this now takes a parameter. There's also a keyword called finally, I think, that is the equivalent of catch with 3 dots. I'll have to re-examine how that works. But try except. This here, the way this works is well, I have an example down here somewhere. Something gets passed back on the stack, okay? It's closer to the bottom. This whole thing should evaluate to a number, like an integer number, that you return from some function. You don't have to. You could just say, you could just put in the value. You put in what you put in here. I'm going to use this as one of the possible values. If I put this value in here, then that means that the code in here, called the handler code, will get executed. Okay? If not, then it won't get executed, and then the system will search down. It has a chain on the stack of handlers, and it'll go to the next handler. So one of the possible values you can put in here, if you don't want to handle it, is I forget the actual names. This should bring us somewhere close. Continue search. You can put that in here. And if you put this in here, then what happens is the processor returns the environment back to what it was when the exception occurred, and places the instruction pointer right at the same spot where the exception occurred, and then tries it. Now, the reason why you might do that is because because something is sent inside here. Okay, the way you always write what I had there, a function that returns an integer value, and then you don't have to, but this is this function get exception information is only valid from here to here. This function get exception information can only be called within these brackets. Nowhere else in your program are you allowed to call that function. You call it, but you're not going to get anything out of it. But if you call that, if that function is called even on its own, it's going to return a pointer, right? Now this except thing doesn't take pointers, right? So this doesn't make any sense. You could say equals 0, and then use one of these defines, something that would work. But the point is, at this point during the execution flow, where something has been interrupted, this function is going to work, and it's going to retrieve a pointer to a great big structure that tells you all about the bad thing that happened. So you invent a function. Everyone does this the same way, and they always give it the same name. Don't know why, but it does make some sense. This is what they call the exception filter. So we take the information out of here and pass it through our filter function, and let the filter function return what to do about the exception. Okay, but at the same time, that filter function might print out information, important data, maybe a stack trace, print out what all the registers had, and so on. Now I have a very simple one here. All it does is print out what's called the context buffer, which has the values of all the registers and segments where the exception occurred. Assuming this flag is set. This is code. It's a number defined, and that's just something in the exception record that gets passed to that through that through that except. At this point, inside here, get exception, or whatever it was called. No, it's not called that. That's what it's called. Here, this makes sense to say. I don't know why that. Okay, I'm going to try to remember where I was. I think this is at this point in the recording, the audio became so bad that I stopped with the previous part, as you probably know by now. It's dropping a lot of audio. Hopefully this won't. Anyway, it turns out this thing is a number defined. And if you look at it, that was fast. It just evaluates to this, where it's just a recast, and this thing here, exception info, is a function. Okay, now I don't know why they define this way, but I don't think that's put in here, or else it would be recursive. Oh, this is no underscore. This got an underscore, so you could put this either one. So my point was, what I did in the previous video was I took that and I put it like this, and I thought that I was doing this. I made a function, just any function, boom, has to return an int, and take this as an argument, and when I compiled this, you'll see I expected that this would work. Whoops, I put boom there. Not realizing that I thought this was just like the actual info, but that's a function. But this should work. And so that's all that. It's not. Oh, wrong place. Look, I'm compiling. I'm compiling programs while I'm recording. See that? Must return. Amazing. Now that proves it, that whatever it was, I turned off something that's been eating up my CPU, because the last few videos, as you've noticed, I could never compile a program. I have to always stop recording. No double click. But still, I assume the recorder is running. It would be funny it wasn't. Well, I guess it's not really that bad. Well, no. This is, typically it never even gets to this length phase. Now, so that's all that evaluates to. This is a filter type function. Now, I don't know if I explained those two return values. It was down here. If this returns that, then the catch handler will get entered. Right? Now, that's what this does. So first, well, let's just verify that this program doesn't enter this part. Okay, with no exceptions or anything going on. It should just print out in try and then quit. It was working. Still, for a while there, it was actually compiling. Okay, Now I can just run it with no debugger first, right? Now, well, that could be it. This could be one of the problems to do with that. All right. Now, so if we cause an exception, the J key doesn't work. J over, I'm going to use J again. So that's a divide by 0, right? That should put it without stepping through the code. If I put a 0 here directly, it will tell me it won't compile or something. You have to fool it, sort of fool it, into thinking that there might be a valid number in there. Yeah. You see, it's still slow. But I did turn this. I had this off for a while, and I turned it back on. So now, if I just run it with no debugger, it should print both. Okay, so it comes into here. F7. And the reason it goes in there is because I asked it to. I was asked to do that. The act of asking is by returning this value. That puts me here. There are two other possibilities. Now, if I do this, I don't know how far I've explained this at this point. What this does is, there's a chain of handlers all sitting on the stack like this, okay, called the structured exception chain or something like that. It's like a linked list. And there's a reason why these things have to be on the stack. And there's a reason why this has to be done in here rather than, say, down here. But I'll get to that in another lesson. But first, what returning this says to the handler, the code that handles this chain, this exception chain, the returning of this value says that I don't want to handle it. Check the next handler and see if they want to handle it. And so this is passing the buck. The question is, what's going to happen if I pass the buck? I'll run it, click F in the debugger, show you what we get. Okay, unhandle exception, and it's telling us what the exception is. Now, so that means none of the handlers said they want to handle it, and so you might guess, and you could guess that correctly that there is a handler that handles all exceptions, and it brings up that box that you just saw. No, that's not the one actually. Sorry, that one is this debugger that installs one handler. But I wanted to show you something before going. The structure that our function obviously is going to get entered because that's how this filter function, how we decide what we're going to return, presumably. And I'll just show you what the structure looks like under the debugger. Show you what we get to work with, to make this determination. And how that would allow us to generate some kind of report and possibly decide what, possibly to return what this one, or the last one, which is sort of the most interesting case. And in fact, I'd like to show you an example of that one, maybe in the next tutorial. So here's the exception pointers structure that is passed along through the chain. It contains two entries. An exception record. This tells us about the exception, the code, various flags. Now this exception record happens to be next. This exception record is null. And so I'll let you think for 3 seconds what this might stand for. Hopefully you've got figured it out by the time I click this. Here is some information about the exception. This obviously is a linked list of some sort, right? So you can have a whole chain of records. Now that ought to be the same. I don't know. I guess no, it wouldn't be the same. No. There's only one the context record here shows what the context was at the time of the exception. All of the values of the registers, what they were at the time. These are familiar numbers to you, should be by now. And ESP, code segment and instruction pointer tells us where it happened. These are the other registers. EBP can be used, that's their stack frame, and that can be used for us to find out the chain of functions that led up to the exception. I don't know about that float save area, but this must be what the floating point unit, what its state was at the time of the exception. The 80 or the 387 or whatever the chip is, floating point chip is, has its own registers, right, and stack and so on. And so this must be its registers. It's a whole bunch of registers. You'll notice they're all single byte things. So I'm not sure how, it says register area. And it might be that this is not formatted in any way. It's just it's an unknown because maybe there are different types of units. They just give you a buffer that contains all of the data that is known to have been in the register arena for that processor. Extended registers. These are some of these, I guess. Well, this is our registers, and there's a hell of a lot here. And some of them seem to have values. I'm not sure what these are. They're not the debug registers. Those are here. 0 to 7. These are called the debug registers. And they don't have any values in them because we haven't set up anything to use the debug registers. You can. Those are special things provided by the processor that allow you to manipulate the kinds of things that might throw an exception, even if they're not exceptional conditions. For instance, you can you can tell the processor that I want an exception to be thrown if there are any attempts to read from some particular block of memory. Like that's what they call a memory breakpoint. You might have a bunch of threads going, and there's a crash that has to do with multiple access of a variable, so you can set a breakpoint, what we call a memory breakpoint, on accessing that variable. That could be useful. So there's lots of information, and one of the things you can do, you might be able to do, it's rare, but it's possible. It might be possible to fix the situation up such that you can continue processing. Okay, now let's suppose we can figure out, I'm going to run up to here and unassemble this, okay? And I'm going to find out what register the division is going to be dividing by. And then what I can do is I can modify that register in the structure so that I won't get a divide by 0 and ask it to return and try again. Now that might in some cases be the right thing to do. It might be critical that for another reason, that the program not halt at this point. And so you're willing to just take a chance. Okay. Now it's going to divide by EBP minus 1C. I could just make it a red. I'll make it easy on myself. I'll do it in inline assembly. You know, I don't know why Microsoft says they're going to get rid of inline assembly. But this is how I learned how this thing works. Without the inline assembly, I couldn't have figured out any of that stuff about the virtual function tables, and calling the virtual functions. And all that stuff about, I was thinking the other day, that you couldn't have, you couldn't have a null value for a pointer to member data in a struct, right? It always came back non-zero, but in fact 0 is valid. The only way to see it is using the assembly, because the language doesn't permit you to put 0 And there were a couple other things that the language wouldn't allow me to do it, so I had to do an assembly just to see. Yeah. Is it? Dude. ECX. Well, actually, I don't mind if this thing overruns, but whatever. Okay, now that should produce an exception, right? And if I change CX to non-zero and then ask it to resume where it was, then it should continue executing without crashing. And then then you bring up a warning box to the customer or whatever, saying the system is in an unstable state, saving off high priority data and shutting down. This would be in a case where it's critical that you don't lose somebody's work that they've been working on for hours. And like say Paint Shop Pro, for instance, you've been working for 6 hours on a teardrop, and suddenly there's a divide by zero. Okay, so let's run up to here. Oh, sorry. I gotta fix the bug first. EP is this it? Yeah, ECX equals 1. There. So suppose I'm able to figure that out, that CXS is the culprit, and I change it to something that's not going to cause a crash, then I should be able to resume that at that point. And we won't go in here. No, how can I should print something out here. Well, we'll just step through it. No, I'd rather put something, because I can't put a breakpoint on nothing. Put func. Do I have put func? Yeah. No. This here too. Dear. All right. Yeah, so normally this just reads as, you'll see most code, it'll read like this. Something exception filter bracket get exception information. And that's all that done. Oh no, right, of course. Now that's another thing I've got to tell you now. But this one, because I'm running out of time. Although I've cut a lot of stuff out of this, so I don't know how long it's going to be. I'm going to have to try and fix my system. I'm going to get rid of this zone line. I think that's the problem. And I got to do a system restore and go back and if there's a record from a couple days ago, and then just go and reinstall the Microsoft, oh god, pain, Microsoft stuff, and then remember which services to disable. Alright, so here we are. Okay, we have 5, and we're going to divide 5 by 0. That should put us here. And SEH should be 0. So this is the state. Somehow we figured out that with the way to repair the problem, we can repair the code by adjusting this value. So we change that to a 1, and we're going to ask it to continue execution. That should put us back here. I'll put a breakpoint there, see if it does. Okay, well, here we are, and CX is 1. So we made it. We fixed the exception and managed to escape and save all the data or whatever. So that's part of it. Sorry about the this problem. Okay, this should have uploaded by now. My virus picture. Hopefully I can fix it quickly and get on with. Alright, same name for ad block. Anyway, brief intro, and you can see what I've been dealing with at the same time. Okay, see you next time.